So in our fourth installment of looking at differentiation, in this video we'll be looking at how and what a stationary point is and determining the nature of that stationary point by either using a table or by using the second derivative. So to get started, what we need to do is understand what a stationary point is. So at a stationary point on a polynomial is basically the turning point of the curve. So at the turning point, what we need to appreciate is that the gradient is going to be horizontal, so it's going to be flat, so therefore the value of dy dx is going to be 0. And if there is a stationary point at point A or AB, if it's got its coordinate, where y equals f of x, then the differential of that function will equal 0. So before we go through some examples, let's just go through the methods and the steps that we're going to follow. Now again, if these steps don't make much sense, then obviously we're going to quote through these as we go through the examples based on two of the most common questions that get asked circling around stationary points. So the first one we're going to look at is finding an actual stationary point. So the first thing you need to do is find dy dx. Then we need to make it equal to 0 because obviously at the stationary point the gradient is equal to 0. Then we need to solve it for x. Now as you can see from the previous diagram, with the cubic graph, that a polynomial can have more than one stationary point. So don't be deterred if you find that there's more than one value of x, because there may be several stationary points in the curve based on the polynomial. Then once we've found the values, the x ordinates of those stationary points, we then need to find the respective y ordinates if the question asked us to find the coordinates of a stationary point. So if the question was related to find the tangent at a stationary point, then obviously you would need to know the x ordinate, but recognizing that it's going to be a horizontal line, so it will just be y equals and then whatever the y ordinate is going to be for that. So it's important that you're understanding of how to find the y ordinate, but also making sure that you're substituting the x value of the stationary point back into the original equation. I can't stress that enough, because like I said, a lot of students tend to go wrong when they substitute into dy dx, which obviously is going to give you 0, and that's not going to be the case. The next thing that we can also get asked to do is to prove that a stationary point exists at a given point. So what I mean by that is if you were given a question to say that, for example, show that on the curve y equals x to the power 4 plus 3x cubed plus 2x squared minus x plus 6 has a stationary point at 6. So if you have a question like that, again, the first thing you want to do is quotes. Now, the key thing with regards to this is quoting these statements. Whenever you're asked to prove something, you always want to back it up with the mathematical evidence. So it's really important that you are quoting what you're using rather than just taking things for granted with regards to whoever is looking or marking your work. So the first thing you want to do is if a stationary point exists, then dy dx is going to equal 0. You then go on to find dy dx, substitute the x ordinate that you've been given in the question, and obviously if it equals 0 then it's a stationary point, and you can write hence the stationary point exists at this point. Or a question might say to you is show that it's not a stationary point, in which dy dx should not equal 0. So let's have a look at some of the examples then. So in the following examples I've just put up the 4 steps that we're going to follow, and obviously hopefully we can relate it to these 5 examples. So starting off with the first one, so what we're doing is asked to find the stationary point. So I'm going to kind of colour code these questions, so if you wanted to forward through the video just to highlight one of these questions that you kind of relate to or one that you particularly stuck on, you can do so quite quickly. So for the first thing we need to look at is the first thing we need to do is find dy dx. I'm going to look at the equation and I'm going to see, is there any fractions, are there any roots in there, because obviously I'll need to convert them using indices before I work out it's a lot easier for me to work out my differential of those expressions. So looking at number 1, there's no rearranging I need to do, so I can go straight into finding my dy dx. So dy over dx is going to be equal to 2x minus 6, and then step 2 is I make that equal to 0, and then step 3 is I need to find the values of x. So in this case it's going to be x equals 3, and then for the 4th step what I then need to do, and again this is just a bonus, and this only because the question's asked me for the coordinates, I then need to find the respective y ordinate. So all I'm going to do is substitute 3 as x into this expression, in which if I work that out I get a value of minus 14, giving me a coordinate of and it's going to be 3 minus 14, and there is that answer. So as you can see, I've followed all of those 4 steps, and there is my stationary point. Now, one thing I could easily do is I could get to a point where I'm writing down a stationary point exists at that, but again, I'm not going to do this for this particular question. We'll go from there. So for the next example, again here, now as you can see, it kind of makes sense in the fact that although it says for multiple answers instead of step 3, it's a case of using your common sense. Now I always say that to do good at maths, it's about 65% knowledge, 35% common sense of understanding what the answer is going to look like. So in regards to question 1, that's going to be a positive parabola, so I'm looking at 1 stationary point. Question 2, I'm looking at a negative parabola, so again I'm looking at 1 stationary point. So as you can see from the equation in question 2, there's no rearranging needed, so I can go straight into working out what my dy over dx is going to be. So in this case, it's going to be 2 minus 8x. Then for the second step, I need to make that equal to 0. So I've got 2 minus 8x equals 0. And then for the third step, I need to solve this, in which I get x equals a quarter. And then the final step, what I then need to do is substitute x equals a quarter into y equals 5 plus 2x minus 4x squared, in which I get a y value of 21 over 4, giving me a stationary point coordinate at a quarter and 21 over 4. And again, writing your answer as a coordinate only because we've said a question might ask just for the x ordinate, which would be worth less marks, but it's always worth just taking a bit of sort of time of reading the questions carefully to make sure that you have answered it correctly. So moving on to example 3, so let's go for a different colour. So for example 3, again, we're looking at a cubic graph. So with regards to cubic curve, we're going to looking for 2 stationary points. So as you can see from the equation, we've got no fractions, no square roots, so we're going to go straight into our first step of finding dy over dx. So if I find dy over dx for this particular expression, I'm going to get 6x squared plus 18x. And obviously the 2 cancels out because it's constant, so it's not going to be a concern. So step 2 is I then need to make it equal to 0. And then step 3 is I now need to solve this. Now, obviously looking at this, again, you might think quadratic, which is fine. Maybe then thinking of double brackets or using a quadratic formula, which is entirely up to you. But for what I'm noticing, I've got 2 terms. They've both got factors of multiples of 6, and they've both got an x. So I can factorize this into a single bracket as x plus 3 equals 0. So either 6x equals 0, in which x equals 0, or x plus 3 equals 0, in which x is going to equal minus 3. So here I've got 2 particular values of my stationary points, and there they are. So the next thing I then need to do, so for step 4, is find the respective y ordinates. So when x equals 0, now remember that we're substituting it into the original equation, not the dy dx, because obviously it'll end up with 0 because that's what y is going to dy dx is going to equal at the stationary point. So it kind of should ring alarm bells to you. So y equals, for this particular example, it's going to equal 2, and when x equals minus 3, y is going to equal 29. So my 2 coordinates are going to be at 0, 2 and minus 3, 29. And there you can see that we followed those 4 steps. So let's now have a look at example 4, which then slowly starts introducing fractions and sort of square roots as we go along. Now, as I said, at your level that you're probably working at this introductory stage, you might not come across this, but all I'm showing you is that if you do get a more extensive question or something that looks a bit more complicated, you just got to stick to your guns and follow the steps. So for this one, let's go for orange. So for number 1, we've got, now I'm going to write down the equation here, so we've got 4x plus 1 over x and I can rewrite 1 over x as x to the power of minus 1. So what I'm now going to do is I'm now going to write this, I'm going to find the dy dx of this version of the equation rather than that. So in terms of step 1, I've got dy over dx is going to equal 4, move the minus 1 to the front so it becomes minus x, and I lower the power by 1, so I get 4 minus x to the power of minus 2. So the next thing we then need to do is make that equal to 0. Now at this stage you might want to think about what does this all mean. Well, if you want to know what 4 minus x to the power of minus 2 looks like, it's going to look like that. So you can either work with this or you can work with this to try and solve the equation. Now some people may prefer in the early stages work with this, however it's not impossible for you to work with that. So finding the x ordinates, now again using that I would for this one. So here we've got, take the x, we've got 4 equals 1 over x squared. Take the x squared over to the other side, so we've got 4x squared equals 1. Take the 4 over to the other side, and then from this we've got x equals plus or minus the square root of a quarter, so x equals plus minus of a half. So we're actually going to have 2 stationary points at this particular stage. So here we've got x equals a quarter, as a half, sorry, x equals minus a half. So then for step 4, when x equals a half, then y is going to equal 4. So I've got my first coordinate of a half, 4, and when x equals minus a half, y is going to equal, and again just double making sure, and I'm not going to be a hero in this one, I'm going to actually type it into my calculator. So 4 times minus a half plus 1 over minus a half, and that gives me minus 4. So here we've got minus 4, so my second stationary point is at minus a half, minus 4, and there are my 2 stationary points. So moving on to question 5, which may seem a little bit tricky because not only does it combine the use of fractions, we've also got a square root in there. So the first thing we want to do is rewrite this using indices. Now there's 1 or 2 ways in which you can do this. You can either think about split, as we've only got a single term on our denominator, you can split this up so we've got this formation. We split the single fraction into 2 fractions, and then this can be written as y equals it'll be x to the power of minus a half, and this, if I just stick a power there, well, 1 take away a half is going to be a positive half. Another way of us working this out is to write 1 plus x to the power of x minus a half, and then if we go on to expand the brackets we would end up with the same expression. So this is what we're then now going to dy over dx because it's a lot easier for us to do so. So if we do just that, so we've got dy over dx, and again moving the power to the front, so I get minus a half x, lower the power by 1 so it becomes minus 3 over 2, plus a half x to the power of minus a half. Now for the second step we want to make that equal to 0, so I've got minus a half x minus 3 over 2 plus a half x to the power of minus a half equals 0. Now you might be thinking to yourself, that looks a little bit nasty. It looks very messy. How on earth are we going to solve this? Because it doesn't look like a quadratic, it doesn't look like a cubic. And again, translating. Now one thing I could do is to rewrite this so that it's introducing square roots in there. But again, I'll be honest, there's no sort of comfort in that because it just seems to get a little bit more weird. So one way of noticing is the first thing we should spot is the fact that I've got 2 terms, both of them have got coefficients, and also they've got powers of x. So what I'm going to do instead is I'm going to look at factorising this instead. So if I take minus a half x out, And again, when you've got powers, you want to take out the smallest power, which is minus 3 over 2. And I set in my bracket. Well, for the first one, I want to take away is just 1. And then I've got minus. Now here, I've got minus because I've got a positive in the original and I've got a minus outside as my factor. And so what we then need to do, so it's going to be still, I've got a half and that'll give me minus a half, that's fine. And that will be to the power of x. Now the reason why it's to the power of x to 1, because if you remember, when we're working with indices, when we're multiplying, because obviously we've been multiplying out the brackets, we add the powers. So I need to think to myself, what do I need to add to minus 3 over 2 to get minus a half? So it's minus, what do I need to add to minus 1.5 to get minus 0.5, and that'll be 1. So it equals 0. Now, trying to go on and solve this, now it's impossible for this to equal 0. So if I just write a half x to the minus 3 over 2 cannot equal 0. So therefore there are no solutions for this particular part. Whereas for this, I've got 1 minus x equals 0. So x equals 1. I've now got my stationary point at x equals 1. And obviously then, if I then wanted to work out the y ordinate for this, so if I just move over here, so when x equals 1, y is going to equal 1 plus 1 over root 1, which is just going to give me 2, which gives me a coordinate of 1, 2. So in this particular question, we're asked to show that the curve y equals x cubed minus x squared, 6x squared plus 9x plus 1 has a stationary point at x equals 3. So the first thing we want to quote on this, that if, so at a stationary point, dy over dx equals 0, because that is what I'm going to be using to show that it's a stationary point. So the first thing I want to do is then find dy dx. So dy over dx is going to be 3x squared minus 12x plus 9. And then what I then want to do is substitute x equals 3 into my dy dx, which again gives me 3 times 3 squared minus 12 times 3 plus 9, which lo and behold does equal 0, so therefore there is a stationary point at x equals 3. So as I say, it's always worth stressing this at the start, because technically just saying that it's equal to 0 doesn't really say anything, it just means it's equal to 0. So it's worth just identifying this key fact before we go on from there. So as you can see, I've showed it equals to 0, so therefore a stationary point exists. Whereas if I didn't include that, you're kind of implying that whoever is looking or marking your work understands differentiation. So it's always worth just making that identified point just to maximise your marks, just in case it is on the mark scheme to give you an accurate mark for that. So the next thing we move on to are the types of stationary points that you can get. Now there are 3 types of stationary points that we can identify. Now the first one, so if you look at this first diagram, we can see that at this point here, let's go for this colour here, so this stationary point, this is what we call a maximum. And if you think back to when we did quadratics and parabolas, again we're dealing with maximum minimum, so this would be a maximum stationary point. This here would be a minimum stationary point. And on the second diagram, this here is what we call a point of inflection. So these are the 3 types of stationary points that you can get, and you may get asked, which is what we're going to move on to next, on what the nature of a stationary point actually is, in which we'll be giving one of these 3 answers for that. So what we're going to do now is show you how you can determine the nature of a stationary point. Now there's one of 2 methods you can use. I'm going to go for probably the one that's probably a little bit more tedious, which is using a table. So as you can see on the screen, I've drawn a very, very faint table, but hopefully I'll show you where this comes in. So in terms of how we go about this, let's start off with a question. So in this particular question, it's asked us to find the stationary points of the curve y equals x cubed plus x squared minus x plus 2 and determine their nature. So not only do we need to find the stationary points, we need to decide whether they are a minimum stationary point, a maximum stationary point, or a point of inflection. Now, some of you may be thinking, well, surely it's pretty obvious. I know that this is going to be a cubic graph. I know that it's going to have two stationary points, and the first stationary point is going to be a maximum and the second stationary point is going to be a minimum, which you are absolutely right. As I said, in order for you to be good at maths, I always say that going back to that 65% knowledge, 35% common sense but it's now just a case of proving it mathematically rather than the use of a diagram. So the first thing we want to do is get a decent colour pen. So let's go for this. So the first thing we want to do is find the stationary points. Now, if I'm just going to kind of breeze through this first stage because we've kind of already discussed this. So first we work out our dy over dx, which is going to be 3x squared plus 2x minus 1. I then go about solving this. So I've got 3x squared plus 2x minus 1 equals 0, which factorizes, or I could use my calculator. So I get 3x minus 1. X plus 1 equals 0. So I've got a stationary point at a third or at minus 1. Now finding the coordinates of those, if I substitute the third and minus 1 back into our original equation, I get the coordinate of a third and 49 over 27. And for the second stationary point of when x is minus 1, I get minus 1 and I get a value of 3. So from this, now again, if I was just do a quick sketch of what this looks like, obviously not that one there, and let's get the pen back up. So if I was to do a quick sketch of what this actually looks like, it would look like something along the lines of that. Maybe without the sort of x-axis, it's kind of distracting, so let's just get rid of that. So at this stationary point here, that's when x equals minus 1. And this stationary point here is when x equals, not minus a third, let's get rid of that, is when x equals a third. And now how do I know that? Because minus 1 is my lowest x ordinate for my stationary point and a third is my biggest one. So further along, that's where we get it. So if I was to draw a line like so, that's where it would be. So again, you can kind of use common sense to determine what the stationary point is going to be, but what we're going to do now is show you how we do this by using this table. Now in this table, what we're going to do is, first things first, now let's start off with our first value of minus a half. So for this first one, so when x equals minus 1, and what we're going to do is we're going to substitute it into this table. Now first things first, what I'm going to do is I'm going to write down the stationary point in the middle. So that's the x ordinate of the stationary point goes in the middle. Now what I want to do on the side of that is I want to pick a number that's just slightly smaller. Now before I move on, it's worth mentioning that I've got two stationary points. So when I pick my two values, I need to make sure that I'm not overlapping the second x ordinate. So here I need to make sure that, and what I need to do is pick a number that is slightly smaller and one that is slightly bigger. But when I mean by going bigger, I've got to make sure that it doesn't go past a third because it will overlap, and that's where it starts sort of making my results a little bit dodgy. So I'm not going to be here. I'm going to pick the nicest number that's smaller than minus 1, which I'm going to say is minus 2, and I'm going to pick the next number that's bigger than minus 1, which is going to be 0. And again, 0 is not overlapping the third, whereas if I was to pick 1, then it would definitely skew my results because it's then moving on to the other. Now what I now need to do is substitute these numbers here into dy dx. So if I substitute minus 2 into 3x squared plus 2x minus 1, I'm going to get a value of 7. Now that gives me a positive gradient, so it means that the line is going to be going upwards. Now when I substitute minus 1, obviously that's going to give me a dy dx value of 0, and that is going to give me a flat gradient. And if I substitute x equals 0 into dy dx, I get a value of minus 1, which has a negative gradient, and as you can see from this diagram here, that it's going to look a bit like an N shape, so therefore it's a maximum stationary point. So what I then need to do is now draw a similar table for a third. So again, rather than, now this is going to end up in a bit of a mess, and so rather than deleting the above, what I'm going to do is I'm just going to draw another table. Just excuse the non-straight lines. So again, starting with my stationary point, which is at a third, and again, I'm just going to pick a number that is slightly smaller and slightly bigger, and try and make your life a little bit easier by picking nice numbers. So I'm going to go for 0 and -1, and again, my 0 does not overlap the second, or the original, the first stationary point of -1. So if I substitute 0 into my dy dx, which again is 3x squared, if I just put an arrow going there, is 3x squared plus 2x minus 1, I get a value of -1. Let's choose a different colour because that's not come out great. Let's go for -1, and that shows a negative gradient, so a gradient that's going downwards. When I substitute x equals a third, that gives me dy dx value of 0, which shows me a flat gradient, and when I substitute x equals 1 into the dy dx, I get a value of 4, which shows a positive gradient. So as you can see, looking at the shape, it's got like a U shape, which therefore means that when x equals a third, or at this stationary point here, it's got a minimum stationary point. And there you go. So it's just a case of, if I had a third stationary point, I'd have to do exactly the same, and we go from there. Another alternative, if you've got a graphic calculator, you could always plot the equations, and you kind of know which value comes first, so you can judge. Put your x ordinates of your stationary points in numerical order, or ascending order I should say, and then from your graph you can determine whether it's positive or negative. But in your exam or in a textbook, they'll be expecting you to show some working out. So it's a good way of using your common sense, using your equipment or your graphic calculator to check whether your answer is correct, but don't neglect proving your answers either by using a valid mathematical proof. So before we move on to introducing the second method, what I just want to do is just sort of go over the steps of what we just done. So the methods to determine the nature of a stationary point by using a table, the first thing we need to do is find dy dx, and that's the first thing we need to do. Then we make it equal to 0, and then we go on and solve it. And so what we're doing here is we find the x ordinates that give us our stationary points. Then we need to draw our table, and then we put our stationary x value here in this box there, and we then go on to pick a slightly smaller number, a slightly bigger number, making sure we're not overlapping the values between the other stationary points. We substitute the values into our dy dx, which is really, really important that we don't forget this, because again, a common mistake that people do is they substitute it into the original equation. And then we then make a note of the direction of the gradients. The middle should be always flat, and then we can draw our conclusions. Now, if one thing we didn't have in that previous example was a point of inflection. Now, if I was to have a point of inflection, let's just say that this is going to be 0. Let's say this was, let's go for 3, and this was 4. Then 3 shows a positive gradient, 0 is flat, 4 is positive. So we end up with something that looks like that, because at this point here, which is our stationary point, any value is going to be positive, and any value on the right of that stationary point is also going to be positive. And likewise, if I went for, let's say, a different set of values, if I had this situation here, so let's say we've got 0 here, and that's going to be flat, and let's say I had -4 and -10, then this is going to show a negative gradient going in that direction, minus 10 is also going to show negative gradient. So what you'll find is something that looks like this, where this is your stationary point. So here you can see I've got negative gradient going downwards, and then I've got negative on the right of that stationary point. I've also got a downward gradient. So that's how we can use the table and this particular method to determine the nature of a stationary point. So there is a second method, and this is probably a more preferred method that students tend to use, and also one that examiners are probably more likely expecting, and they probably ask you specifically to use the table method, and if they don't use that, they probably expect you to use this one because there's less faff and you don't have to draw a table, which is using the second derivative. Now another way of finding out the nature of a stationary point is by using the second derivative, and if you work out what the second derivative is and the value of when you substitute the value of the stationary point is less than 0, it gives you the maximum, which kind of goes against your thinking. Now when you think of a number that's less than 1, you think, oh, that's a minimum, but actually in this case it's a maximum. If it's equal to 0, it's a point of inflection, and if it's greater than 0, although your common sense might be thinking it's a maximum, actually it's a minimum. Now if you're not too sure about what the second derivative actually is, now the second derivative, not using proper English or math in that case, is basically dy dxing the dy dx. So you're kind of differentiating twice is basically what the second derivative is. Now what I'm going to do is I'm going to go through an example, and we're going to use this sort of theory and show you how we can determine the nature of a stationary point. And also what I'm going to do, just to save a bit of time, I'm going to use the exact same question as I did for method 1. So going through this question, the first thing you want to do is work out dy dx, which in this case is 3x squared plus 2x minus 1. You then want to make that equal to 0, so just to save a bit of time, I'm going to go straight into factorising, make it equal to 0, and then find your x ordinate, so it's going to be add a third or minus 1. And then obviously if you wanted to work out the coordinates, you can do, so we add a third, 49 over 27, and minus 1 and 3. Now the key thing to establish is these two numbers here. Now because obviously the y ordinates are only there just because we've asked, if it's asked us to work out the coordinate, then we need to give the coordinates. If not, we're happy with the x values. Now to determine the nature of this, all I need to know are the x ordinates. So starting off with, so if I start off with when x equals minus 1, so if I work out the second derivative, so if dy over dx is equal to 3x squared plus 2x minus 1, then the second derivative, which we write as d squared y over dx squared, is going to be 6x plus 2. Now this is my second derivative function, and again I've achieved that by dy and dxing the dy dx. So when I then use that second derivative function, so when x equals minus 1, d squared y over dx squared is going to equal, when I substitute minus 1, and it's going to equal minus 6 plus 2, which is minus 4. So as the second derivative is less than 0, then that's going to mean a maximum stationary point. And when x equals a third, then my second derivative, when x equals a third, is going to equal, well, 6 times a third gives me 2, 2 plus 2 gives me positive 4. So as the second derivative is greater than 0, it's a minimum point. Don't know what I've written there. So it's a minimum stationary point. And one thing I forgot to add here is when x equals minus 1, and here it's when x equals a third. So as you can see, a lot of people tend to go for this method simply because we don't have to have any recollection of the graph. We don't need to do any tables. We don't have to do further substitution. We can just work from as it is. So, and there you go. So now working through the steps, if I just, and again, it's worth making a note of what those steps are for this particular method, which if I just scroll down, which are just here. So you might want to make a note of these, or let me just go over what we did for this particular method. So the first you want to do is find your y dx, make it equal to 0, and find the x ordinates of your stationary point. If a question asks you to find the coordinates, make sure you find the respective y ordinates by substituting those x values into the original equation. The next thing you then want to do is find the second derivative, and then the next thing you then want to do is, and again, I can't stress this enough, a common area that a lot of students go wrong is you want to substitute the x ordinates of the stationary point into the second derivative, and then what you then want to do is quote one of these. So this is something that you're going to need to remember, and it's certainly worth quoting in your answer whether the second derivative is either less than 0, equal to 0, or greater than 0, and what that means. And as I said, that final step is just make sure you quote one of those lines. Hopefully this all makes a bit of sense. Sorry if I've gone on and repeated myself quite a lot of times. If you have any questions or would like a worksheet on this particular topic, feel free to drop me an email at 162maths@gmail.com.